I will tell you 50 years ago, when most of you have not been talking about the work that Peter Mueller did on wave-induced viscosity. 50 years ago, his paper was published, and I could say that if you are working on wave-medium interaction, you should look at this paper. It's very elegant and needs attention. However, while Peter was able to show that the wave-induced momentum transfer is down gradient mean shear, so he could define the viscosity. This viscosity turned out to be orders of magnitude too large. It was about 0.5 meters squared per second, while normal viscosities are at least 2 or 3 or even 4 orders of magnitude smaller. It was never detected in wave mean flow correlation analysis, as we will see on the next slide. But a mistake was never detected in Peter's theory. So I thought it would be worth to look at this theory again. Shortly after Peter published this paper, Gary Joyce and Claude Franquin started to look in ocean data and calculated viscosities. And they turned out to be either insignificant or very low. Later, Claude Franquin take up this problem, and he found the viscosity of 2 times 10 to the minus 3, which is 2 orders of magnitude smaller than Peter's value. I could not find more recent papers, so I asked ChatGPT, and he came up with, or she or it came up with viscosities which are very small. Here, very small compared to these values. And then it alluded to a Garrett-Munk spectrum that was due to Garrett-Munk. And actually, the Garrett-Munk assumption is also a major thing in Peter's theory, and it turns out to be wrong. So let's see if this is correct. We start very simple with single waves instead of a whole spectrum of waves. For a single wave propagating in a mean flow, what we call action is an anisotropic invariant. Action is energy over intrinsic frequency. And so if you convert, if you convert action conservation to energy conservation, you come up with that the energy is changing according to this relation. The essential thing is that the intrinsic frequency of a wave propagating in a mean flow is changed because it's governed by that the intrinsic frequency is the Doppler shift, and d by dt of the Doppler shift is then related to the gradients and the angle of the horizontal wave vector. So the C appearing here will go through my whole theory. It's essentially the shear but multiplied by the angle of the horizontal wave number with respect to the x direction. Let's start actually with very simple waves. An upward propagating wave and a downward propagating wave. Up is for plus and down is for minus. Both these quantities change, and the equations are here. They are such that energy over intrinsic frequency action is conserved. And so here you see a numerical ray tracing analysis. An upward wave is bouncing up and down in the water, and a downward wave starts first downward, and then it's also bouncing up and down. And the energy and the intrinsic frequency, they follow that. Movies all know when energy is increasing, also the intrinsic frequency is increasing, that it should be when the action is conserved. The essential thing is that the time scale of this exchange relates to the shear, and for a moderate shear of 10 to the minus 4 per second, you find a time scale of a few hours, and downward bouncing and change of energy and intrinsic frequency. Now, of course, these waves would interact because you have non-linearity. And so let's see very simply what happens when you introduce an energy exchange between these two waves. So whenever the plus wave has more energy than the minus wave, you give a little bit of the energy to the downward wave, and vice versa, with a time scale which is oriented at wave interaction time scales. And so if you define the total energy and an energy asymmetry, you get two equations which are coupled. The asymmetry is now bent according to this exchange process. For long times which are large compared to this tau r time scale, you can forget about the time derivative in the second equation. And then you end up with an energy equation which reveals the viscosity. Energy is change is given by the viscosity times the square of the shear. And the viscosity is actually related to the energy and this time scale. And if you implement reasonable values, you get these large viscosities that Mueller has found. Now, Peter's theory was not for a single wave, but for a whole spectrum of waves. So you have for the vertical dimension, and the vertical wave number, which is positive and negative. Positive wave numbers have downward propagation, and negative wave numbers have upward propagation. And so what you can do, you can define a symmetric part of that spectrum, an asymmetric part. And the symmetric part, if you integrate it, yields the total energy, and the asymmetric part would yield the energy symmetry. Instead of these action conservation equations for single waves, in the spectral environment, you have the radiation balance, which can be broken down to a conservation of energy. And if you write this conservation of energy for the symmetric part and the asymmetric part, you see that these are coupled. The energy of the rate of change of symmetric part is forced by terms with the asymmetric part and vice versa. Here on this side, you have this wave mean flow interaction term, which we had before. But in addition, you have now propagation terms, refraction by the mean flow, dissipation, and this relaxation term. So we are dealing with this equation further, and actually we start to integrate that. So first, we assume that the steady balance is assumed for the symmetry. So we neglect this term. Next, we factorize the spectrum, which is just Mueller of finding total amplitudes of the spectra. And here, this shape functions. The shape function is assumed the same for these two things. You can use different one, and here it's a little bit more complicated, but not really different. Next, we integrate the spectral balance over vertical wave number and frequency, and assume that this relaxation time scale entering here is constant. Then you end up with balances for the amplitude E, which is the total energy, and for the energy asymmetry. Here you have these two things. Coefficients appear, the mean group velocity for the vertical propagation. For the wave mean flow interaction term, you have an interaction coefficient called lambda here, which is the frequency independent function. And then you have a dissipation and relaxation term. So now we do the same as for a couple of our waves. We assume the symmetry balance to be steady and eliminate the asymmetry from the balance and we get an equation for the energy, which is fairly long. We have it on the next slide again. So the energy is governed by this equation here. And what you see is the diffusion term, two derivatives of that, appears. And this is because the former equations have an interlacing way of the propagation terms. Diffusion equation and things like that. Then you have advection terms, this one and this one. I have one derivative of that. Then you have the gain of energy due to the interaction of the mean flow, and this gives a viscosity we will see, and then you have a dissipation term. So what Peter did next was to assume, and this is a crucial and basic assumption, and I say again, this is for this all the problems. He assumes the energy spectrum is isotropic, and this was guided by the observations of Garrett-Munk state in the ocean. The Munk spectrum describes most of the variants of entire waves, and is isotropic. So Peter did this here also. And then if you do that, of course, this term here, which has a cosine of phi, and this term also, which has a cosine of phi, times an isotropic state, if you integrate, the cosine integrates to 0, and so these advection terms vanish, they are absent. And so we end finally up with an energy of the isotropic state, which has diffusion and this viscosity. And if you then proceed and use GM parameters, you end up with, also for the spectrum model, you end up with this enormous viscosity. So it's a construction of the viscosity. It's a time scale times an energy. And then this is a coupling coefficient of eddy mean flow and direction, and you have it here on the right hand side. You can calculate. It's a function of n over f, and it's basically 0.04. So it's a fixed function. But if you enter and gives the rate the state of the Garrett-Munk model in here, you end up with this large viscosity. So what can be wrong in Peter's theory? And just to make this short, it starts with the action balance and three-dimensional propagating rays. I was not object that this is a description for some regional state. And n constant and this relaxation time being constant is not a crucial thing. To the lowest order, I should give some numbers which are reasonable. What is really the problem is the isotropy of the wave shape, the GM shape of the spectrum, and boundary conditions are entirely absent. There's no, in the theory, there's no vertical reflection at the surface or the bottom of phase point. So let's see what we can do. I define the simplest spectral model. I start again with equations for symmetric and asymmetric state, again factorized by amplitudes E and delta with some phase shape functions. To make it simple, I assume that the current is unidirectional, and I also assume that the shear is constant. And so all the other parameters which will appear are also constant, and I do this because I know how I can solve linear equations with constant coefficients. You can go away from these simple things and make some extensions, and you can end up with the same thing. Then you have the vertical boundaries. Yeah, at the top, the bottom, the wave state would be symmetric if there's no forcing. Upward waves would just be reflected into downward waves. So exactly at the boundary, the delta should be 0. But when you have a wave maker at the top or bottom, you have that force at the surface and the bottom. This may be the wind, and this may be tidal conversion. Making this exactly mentioned, there's another time scale is introduced, which is a propagation time scale for vertical propagation in the water. And so, again, to make it simple, dissipation is assumed to be linear with the dissipation time scale. So then the reduced equations here have 4 time scales: relaxation of vertical symmetry, vertical propagation, interaction with the mean flow, this U prime term here, and the dissipation term. Yeah. So you have if all are constant, I can solve these equations, of course, and this is what I'm going to do. So again, you end up with these equations here: propagation, rate mean flow interaction, dissipation, relaxation, and boundary condition. Now, if you in these equations, if you assume that the wave state is isotropic, we end up with Peter Mueller's problem. But you can show that these equations are intrinsically anisotropic. The cosine of the direction of the waves entering here makes the solution of the spectrum anisotropic. And so what you can immediately see, the solutions of the form, you have an amplitude and a vertical structure function, which is exponential. It has this cosine phi in here. If you introduce this ansatz here with this pi function into these equations, you end up with an equation for the habit of the amplitude variables where no that's a point here. Where no indication of the mean flow is present, all mean flow dependence is via this exponential vector. This function here, of course, can be easily, this problem easily solved by signing hyperbolic or cosine hyperbolic functions with this boundary condition. So it's easy. The next slide shows my solution. The wave spectrum, which is still a function of phi and z, depends on z and on phi, and it's anisotropic. It's positive here, negative here, and positive here. So it's basically anisotropic. So the whole thing can be solved in this constant coefficient world without any problem. Let me see what happens next. The E hat is, of course, not the energy of the system. The energy of the system, you integrate it over all the wave directions, and then you end up with the integral of this phi function. And it occurs that this integral of this function is a Bessel function of we go all up. So the energy is related to this amplitude and this Bessel function term with the arguments of this phi function. Scaled z, propagation time, wave interaction coefficient, shear, and wave direction. Yeah. For this E, you can derive easily from the previous equation an energy balance. And what comes out, E by dt of E is equal to some kind of diffusion term now with this Bessel function in the kernel. And the wave interaction term, because it has this cosine pi in there, ends up with the first order Bessel function. Yeah. So this is a energy balance of the wave in this anisotropic state. It's non-GM, it's really anisotropic. You can show that this term here is the work of the wave-induced factors of buoyancy and momentum working on the mean shear. This is a normal kind of exchange between the wave and the mean flow. So this energy which is lost or obtained here for the wave field is coming from the mean flow. You can show that this is true by evaluating the wave-induced stress, the residual form, adding momentum flux and buoyancy flux. You can see that this flux depends entirely on the asymmetric wave state in the vertical. And because of this cosine and phi, it should also be anisotropic. So the anisotropic vertically asymmetric state determines this exchange between wave and mean flow. We can go further and evaluate that. And then we find that the resonant residual wave mean flow flux is given by this lambda function and this integral, which is the third order. That's a function term. So everything is consistent here. Now, the Bessel functions which I have introduced is I0 and I1, I0 for the energy, and I1 for the wave mean flow and change term. And you see that for the main wave mean flow change term, you have a very low arguments here, less than 1. You have a linear regime. And if you expand that linear regime, you find that the residual momentum flux is equal to a term proportional to the shear, and this term proportional to the shear is the viscosity. Look at this viscosity. It's constructed as the Mueller one, but the essential thing is that it's not the energy of the wave. GM states the symmetric large energy, and thus the energy of symmetry. If you put it in reasonable numbers, you get viscosities which are 4 orders of magnitude below Peter's value. So whenever you look in the ocean and correlate flux data with shear values, you would certainly find these values here, and this explains why the failure has been found in the observation paper. So this actually ends my the presentation here. The energy spectrum includes the free flow is intrinsically anisotropic, and it is not GM. The large viscosity of Peter always appears if you write the equations in these variables, but it's actually cancelled exactly the other terms that are propagation terms. So there's an intrinsic balance in there. If you write the balance correctly, you find another viscosity which is 3 to 4 orders less than the problematic state of that thing. So again, Peter did not do very much wrong. What we assumed at the end was isotropy. In isotropy, if you look at the real equation, the spectrum is not isotropic. And the anisotropy makes this whole thing failure. Finally, let's see what you see again, these diffusivities. Peter's diffusivity is the time scale times isotropic energy, very large. Our model is the time scale times energy asymmetry, actually as it should, because the residual momentum flux, as I said, depends on the anisotropic asymmetric state of the wave field. The total energy does not enter at all in that. So at the end, GM of that spectrum, ZQT is correct concerning the magnitude of viscosity, so it was unable to, with my limited ability to go around with these things, it was unable to give me references for its correctness. But it's totally wrong concerning the GM, so that's all.